Hello. Our application is ChatGPT on phone, and our team members include me, Sai Rahul Reddy Kondapudi, and this is Neeraj Gopalakrishnan. When it comes to the course project requirements, we have developed, implemented, and tested an internet application with client-server architecture. And for testing the application, we deployed it on various servers all around the globe to test its latency and throughput. Furthermore, we benchmark the application with diverse network conditions such as Wi-Fi, 4G, and 5G. When it comes to the new design algorithm that was required for this project, we tested our application with audio compression before transmission over the network.
So over the course of our presentation, we'll be taking you through the following aspects of our project. The first one being the fundamental concepts that are relevant to our project. Secondly, we'll be taking you through our bad implementation of our ChatGPT Android application. And third, we'll be talking about the integration of audio compression with this bad ChatGPT application. And finally, we'll be going over the benchmarks that we conducted for this project and come up with insights for them. So, starting off with the fundamental concepts of our project, our project utilizes a client server architecture where there's a mobile application that communicates with the server, and this server processes our ChatGPT queries. So another reason why we chose this type of a client server architecture is because while benchmarking, we deployed a lot of servers all around the world, and this type of an architecture simplified the process for us.
And when it actually came to the usage of the large language models, we had a lot of options, but we decided to go ahead with OpenAI because this has been tried and tested for a year, and on top of that, it provided us with free credits. And this also, along with us talking with the language models with one-on-one queries, we were also able to have long, persistent, stateful conversations with the model.
So, so firstly, for speech to text, where our input to our application was speech audio sample. So for speech to text conversion, we used OpenAI's Whisper ASR, which is a model which is utilized a lot for automatic speech recognition. The model we used was a machine learning model which had close to 39 million parameters, and which had a minimum requirement of 1 gigabyte of VRAM. So we integrated this Whisper API into our application, which basically helped us convert input audio recordings into text on the server, which is then used as input to our GPT 3.5 model.
Similarly, when it comes to text to speech, we used Expose Speech Library to convert text messages that we received from OpenAI. And we had various options to choose for the text to speech functionality, and some of them were Tacotron, WaveNet, and Transformer. But we decided to go ahead with Expose Speech because of its lightweight runtime.
So, coming to our the part where we have new design. So as mentioned earlier, we are basically compressing our audio files. So we compress our audio files before we send it over the network, and this helps us with to achieve faster data transmission times, and also to reduce the latency of the network. So we converted our audio, input audio files into the Opus format, which helped us achieve this low latency.
And we also decided to use AWS EC2 instance for this because, as we earlier mentioned, that we were planning on benchmarking by deploying the application itself on around various parts of the globe, and EC2 instance will help us like deploy this application in various parts, also across the transoceanic links. Now we'll be diving deeper into the implementation details of our ChatGPT application. So this is the overall application architecture of our project. So when you see the right side part, which is the mobile application, so it starts off with the audio recording interface. So here the user will be able to click on a button and record an audio. And instead of the audio being saved onto the device, this will be channeled into a pipeline, which will be then taken as an input to a post request and be sent to our AWS EC2 instance. And when this audio file is received on the server, the first thing that will be done is Whisper API will be utilized in order to convert this speech into the text. And once the speech to text conversion has been completed, we'll be using the OpenAI's API keys and send this text to GPT 3.4 large language model. And then we wait until the OpenAI server provides us the answer to what our answer to the question that we have provided it. And once the answer has been generated, we use another post request to send this back to our mobile application. And when the mobile application receives it, it's going to be utilizing the Expo speech library in order to like give an audio output for the result that we have received, and simultaneously the text of the chat will also be displayed on the screen.
So as you can see over here, we have provided an example of our front end. So we developed our application as a React Native application where we have provided a facility to record audio. So when we record audio using this facility, this audio is sent to our server using a post request. And after all the processing is done on the server side, we receive a response as text, which was basically an output, the output from our GPT 3.5 model. So this text is then converted into audio and displayed in our front end. So we also have an additional facility where, apart from recording and displaying audio, we also display the text corresponding to it, and the Expo speech library does this for us. And on the back end, what happens is, as explained before, we receive audio samples from the mobile application. These audio samples are converted into text using OpenAI's Whisper, and this text is then used as an input to our GPT 3.5 model, and the output from our GPT 3.5 model is sent to our client as a post request. So now we're going to be talking about our new design where we integrated audio compression into our bare minimum ChatGPT application. So contrary to what our architecture was before, our updated architecture is such that after recording an audio sample, it is compressed on the client side. So we perform compression of whatever the audio format was into the Opus format, and this Opus file was then sent to our server, and decompression of this file is done at the server, following which like the usual processes where speech to text conversion is done using OpenAI's Whisper, and then this text is put in as an input to our GPT 3.5 model, and after which this text is then sent back to our mobile application and it's converted into speech using Expo speech. So the main difference between our bare app and our updated app is that compression is performed in the client side and decompression is performed in the server side. So yeah, so audio compression is performed in the client side where it's compressed to the Opus format, and instead of MP3, and the key difference is that it is this Opus format that is sent from the client to the server instead of MP3. Our assumption was that compression leads to faster data transmission and reduced network latency, and this was the reason why we attempted this. Done.
Now we'll be discussing about the fourth and the final part of our application, which is the testing and the analysis part of it. So when it came to the real world testing, we were able to deploy our application on three different EC2 instances, and the three instances that we chose were Ohio, California, and Mumbai. There's a specific reason why we chose these three. Are obviously the distance is a main metric for this, with the Ohio being the closest to the current location that we stay at, and California being on the West Coast, and Mumbai being all the way across the United States, and where the transmissions have to take place via transatlantic communication. And for these in specific, the metric that we have chosen to measure is time, because the amount of latency takes is of greater impact for these kind of applications. And the different network conditions that we've tested on this application is on our home Wi-Fi one, and we've also used 4G in order to test this. And when it comes to the benchmarks, we've utilized two formats. The first format is the WAV format, or the uncompressed format, and the second one is the Opus format, which is the audio output, which is the audio file output format that we'll get after compressing. So both of these have been used in our benchmarking scenarios. And so in the following slide, we have compiled together two different plots, one with 5G and one with 4G and one with our home Wi-Fi. So as you can see here, the plots have been presented in detail for all the three instances, California, Ohio, and Mumbai. And the number one thing that straight up catches our eye is the latency time for Ohio being very less, because our current location is very close to Ohio. And the second one also, the second thing that catches our attention is gonna be Mumbai, because Mumbai is all the way on the other like part of the it's like completely different country across the oceans. Therefore, the amount of latency it's gonna take is way more when compared to the Ohio's. And same goes with California. There's not as much latency, and it's not as low latency as Ohio, but these numbers make sense for the distance when compared to the distance from where the benchmarks have been conducted. And the second thing to note is the difference when it comes to the latency of compressed file versus no compressed file. So this effect can be majorly seen with the Mumbai instance, where there's a lot of difference between the uncompressed and the compressed file. And similarly, a certain amount of difference can also be seen for Ohio and California. Now, when we look at the plots that have been generated for 4G, again, the first thing that catches our attention is the Mumbai's instance. So we can see how the compression and no compression made a large amount of difference for this. And for California and Ohio, yes, there's not a lot of difference for this. And when you compare the latency times that it took for 4G and 5G, we can see the difference. We can see that there is a noticeable difference. So first, when it comes to the California instance, the compressed time increased from 137 to 155, and the same goes for the Ohio instance. On 4G, it being close to 69, which has fallen down to 67 for the Wi-Fi, and as expected, similar results follow for the Mumbai instance.